Hello, and thank you for joining today's webcast. I'm Lisa Arrigo with SA International, your moderator for the next 60 minutes. During this program, you'll hear from two experts who will discuss how certain materials and designs can be used to help vehicles pass the Insurance Institute for Highway Safety's Overlap Crashworthiness test. Our speakers are Becky Mueller, Senior Research Engineer with the Insurance Institute for Highway Safety, a nonprofit organization dedicated to reducing deaths, injuries, and damage caused by crashes, and Mansoor Murdamati, Chief Engineer at Dow Automotive Systems. This webcast will also include an audience Q&A. If you have questions for our speakers, please submit them at any time by using the Ask a Question box on your screen. You may also use this box to alert us to any technical difficulties you might have. However, if you do have trouble seeing the presentation, make sure your pop-up blockers are disabled. You may also download PDFs of the speaker's PowerPoint slides by clicking the links on the left-hand side of your screen under Event Resources. Please note, this webcast will be archived on the SAE website. An email will be sent to all who register for the program as soon as the archive is ready. And now, to kick off our discussion today, we have a poll question for our webcast audience. Actually, it consists of two questions. Let's bring those questions up on screen. The first question is, which of the following do you think is the most important way to improve crashworthiness? Please select either strong occupant compartments that won't collapse in a crash, effective crumple zones to reduce the forces on occupants, use of energy-absorbing fender structures, or frontal airbags for drivers and passengers. The second question is, when did frontal airbags for drivers and passengers become standard on U.S. vehicles? Please select either 1999, 2003, 2007, or 2008. Please make your choices now. We'll review the results later in the program. And now, it gives me great pleasure to introduce our first speaker, Becky Mueller. Becky is the lead engineer for the Insurance Institute for Highway Safety's Small Overlap Frontal Crash Test. Since 2011, her projects have focused on crashworthiness, biomechanics, front and side crash protection, test dummies, and injury biomechanical criteria. She previously worked for the National Highway Traffic Safety Administration on projects related to car safety regulations and prototype dummies. Hello, Becky. Welcome to our webcast.
Hello. Thank you so much for this opportunity. So today we're going to be discussing the IIHS Small Overlap Crashworthiness Test and improvements that manufacturers are making to their vehicles. So a little background about our test. Our Small Overlap Crashworthiness Evaluation Test began in 2012. Since 2012, we've tested over 135 vehicles. And these vehicles have been in a range of different sizes and classes. So we've already covered everything from mini car, mid-size car, luxury cars, small and mid-size SUVs, and even minivans. We've also already tested 18 models twice due to the fact that manufacturers have already come up with redesigns to improve their performance. Out of these 18 models that we tested twice, 16 redesigns improved in their structural rating, and 16 of these models also improved in their overall rating. So very promising. We don't have a ton of detail about exactly what manufacturers have done to make changes for small overlap, but what we can do is look at different categories and different components of of modifications to the structures for small overlap. And so here's a diagram showing some of the main components that manufacturers are using to strengthen or to change performance for small overlap. So we've got things in the very front of the vehicle attached to either the bumper beam or the engagement structures attached to frame rails that are shown in green. We also have structures shown in red here that are that shotgun or side member structures that have been modified in one way or another. We have areas also surrounding the occupant compartment, things like the firewall, the door frame, all the different components of the door frame, the floor, things like this. And we also have some other components that manufacturers have indicated they've changed that we can't picture on this diagram. So things like door beams, seat mounts, steering columns, and stuff. So through this study, we're going to be counting these components and trying to understand what effect these components seem to have on the overall performance. We've been able to identify some visible modifications in these 135 vehicles that we've tested so far. And they tend to fit into a couple of categories. So just as we looked at the previous diagram and categorized structures, these are some real-life pictures and examples of these different categories. We have engagement structures that are attached to either the frame rail or the bumper beam. You can see these on the upper and lower left. We have shotgun structures, so these outboard frame members that are strengthened or attached in different manners. We also see some evidence of occupant compartment reinforcement, extra layers of metal, extra components that seem to add strength and rigidity to the vehicle. So these are all things that we're able to easily identify. These components fit into different categories of performance. And so we know that structures around the door frame and in the occupant compartment are typically used to reinforce the occupant compartment to create a stiffer structure so that there won't be as much deformation. We also have observed that the shotgun structures, pictured in red, typically are an energy absorbing load path. And we can see this through some of our acceleration data. And then structures on the front end of the vehicle, these green extension structures, tend to provide early engagement of the frame with the barrier and also initiate some lateral motion of the vehicle. So here are 16 models that we tested before and then again after design changes. So we'll be looking at these different categories and making some observations about these vehicles. What's kind of cool is that we have in this subset of vehicles everything from a mini car all the way up to midsize SUVs and a minivan. So we're not just looking at patterns that we're seeing for one particular size or even manufacturer. So if we do a tally, basically counting whether or not a vehicle had a modification to a given part that we identified in our second slide here, this gives you an idea of where we're seeing the most popular design changes coming from. And what you'll notice is that all of these vehicles, all 16 of these vehicles, had at least one component of the door frame that was strengthened. So this seems to be one of the main strategies by manufacturers, is to really strengthen that occupant compartment to be able to withstand the crash forces. What we also notice is that manufacturers tend to tune their vehicle to their individual needs by adding some of these other components, whether it be bumper beam or subframe extensions, shotgun structures, or various other strengthening to the occupant compartment that we see there. But in general, the main trend is to strengthen that occupant compartment. So what we were able to do is compare the number of areas that were modified to the improvement in the vehicle performance. So the reduction of structural intrusion. And what we see is the trend is that the more areas that are modified on a vehicle, the lower the intrusion levels get. So it's more promising. So if you've got a vehicle that has a lot of structural problems, the more things that you modify on it seems to correlate to better performance overall. What we've also observed is that these designs produce different vehicle-to-barrier interactions. About half of the vehicles that we tested have one of the two of these categories. So either vehicles rotate about the barrier or they translate away from the barrier. So we see a lot of vehicles that rotate around the barrier also exhibit larger delta Vs, typically in the 45 to 60 km/h range. Vehicles that translate or glance off of the barrier tend to have smaller delta Vs. We see in a range typically of 33 to 50 km/h. So we're going to look and see if there's any patterns between the type of motion that the vehicle has and some other observations about these countermeasures. One thing that we noticed is that vehicles with the shotgun load path tend to rotate around the barrier. And what we also see is, because we know that these shotgun structures are used for absorbing additional energy, we see increases in our peak vehicle accelerations and our delta Vs. So we see a much stronger occupant compartment, but also greater crash forces in these cases. Now, what does this mean for dummy kinematics? What we know is that vehicles that are going to have higher crash forces are going to put a higher load on the dummy restraint system. And so this is an image of what we typically see. As the dummy moves forward, his head tends to rotate when the vehicle begins to rotate. But the good news is that he's staying within that perimeter of those airbags. He's not moving too far outboard, but he is facing possibly higher head and chest measures because of the higher crash forces. So in most of the vehicles in this category that rotate about the barrier, we see that the vehicle manufacturers provided an adequate restraint system to protect the dummy based on dummy injury measures and the restraint system performance. But we did see that in 3 vehicles, we had high vehicle G and delta Vs that contributed to the dummy striking the steering wheel through the airbag. So what we think is that the restraint system design is definitely important and independent somewhat of the structure. So it needs to be considered separately, that not everyone is acing the test immediately by improving the structure, but that proper restraint system tuning is very important. Now if we look at the other category of vehicles with more lateral translation. These we found to typically be vehicles with these engagement structures, those structures attached to the bumper beam or the frame rail that initiate a lot of lateral motion. And so the picture here we have shows a vehicle before and then after design changes, and at about the 200 millisecond mark, this after design change vehicle with the engagement structures had 11 centimeters of additional translation away from the barrier. So it really glanced off more than the original. What we typically see is lower peak vehicle accelerations and delta Vs when the vehicle translates away from the barrier. And this is because the vehicle is not engaging for nearly as long and not crushing backwards as much. And so we're seeing lower crash forces. Well, again, what does this really mean for the dummy inside of the car? In vehicles where we see a lot of lateral translation away from the barrier, we also see a lot of outboard motion of the dummy. So as the vehicle moves away from the barrier, the dummy is also moving in the opposite direction, heading towards an area where airbag coverage isn't always guaranteed. So in general, most of the manufacturers have done a good job of keeping the dummy within the perimeter of airbag protection. But we have seen a few examples where there's so much outboard motion of the dummy because the vehicle translates so much that the dummy does slide off the airbag and into a gap in airbag protection. But what this suggests is that, once again, structure and overall performance are not directly linked, but that you also need to consider the restraint system performance for the given vehicle motion that that vehicle is having. So you can't just design a restraint for everything. What we saw in these vehicles is, because we tested them before and then after design changes, we were able to compare the weights of these vehicles. Now keep in mind that some of these vehicles have been complete redesigns, have had other components within them changed between the two model years. So for example, the vehicle like the Rogue pictured here was a complete redesign. So seats are new, interior is new, wheels are different, fascia is different. So some of this weight is not related to small overlap. But the important thing that we wanted to capture is that small overlap changes to improve performance from something that's a failing grade to one of our passing grades and our award winners does not require tons and tons of weight. And that even if it does add weight to the vehicle, manufacturers are being very smart about finding other ways to reduce weight, either in seats or in comfort creature features and lightweight hoods and lightweight other components that make the vehicle almost the same, possibly even lighter after the redesign than before the redesign. So what we found is that the curb weight change is not really related to our structural improvement. So to summarize trends from this first half, from our paired vehicles, the number of modifications are related to the reduction in intrusion. Occupant compartment was strengthened for each vehicle, so it appears to be one of the most important aspects of improving performance for this test. Engagement structures tended to induce lateral translation. Heavy reinforcements of the occupant compartment typically resulted in higher vehicle accelerations and delta Vs. Dummy-based evaluations required both structural improvements and consideration for proper restraint system tuning. And there was no correlation between the weight change and improved performance. So like I said, we have studied we've tested 135 vehicles, of which only 16 we had before and after design change comparisons. We wanted to be able to do something where we can understand what's going on with the rest of the vehicles. So we're going to look at some trends for vehicles that we tested only after vehicle modifications. So this gives you a distribution of the vehicles that we've tested that have design modifications, but we've only tested once. So again, we've got a range of vehicles all the way from mini car, tons of midsize cars, small SUVs, large cars, midsize SUVs, and minivans. So we've got 13 manufacturers, 53 vehicle models with structural changes that we're going to be looking at here today. Again, if we tally which components were modified on these vehicles, of the 53 vehicles that we have redesigns for, 52 out of 53 vehicles modified at least one component of the door frame. And this is consistent with what we've seen from the before-after pairs, that this seems to be a very important component for redesigning vehicles. We also see a lot more other things. So about a third of the vehicles also have bumper beam extensions or subframe extensions. Also about a third have shotgun structures and some other strengthening of the occupant compartment as well. So when we look at the combinations of these countermeasures and what their overall performance ends up being, what we see is that the more types of countermeasures that are instituted in a vehicle, the better the structural performance tends to be. Now, it's not exclusive, but what's very interesting is that for the good rated structural vehicles, this is the only category where manufacturers have used all three types of countermeasures together on a vehicle model. Now, it doesn't have to be that they use all three, the engagement structures, the shotgun structures, and the reinforcement of the occupant compartment. But this seems to be providing the best structural results, is to try to use all of the strategies, which is also very consistent with what we observed with the before-afters, where the more things you change, the better the overall outcome. So, and it seems that the vehicles that are still kind of struggling getting either the marginal or the poor ratings are those that aren't using nearly as many components. So, what we've also observed here is that similar types of countermeasures can produce different vehicle motions. So both of these vehicles had good rated structures, had all three components that they used: engagement structures, shotgun load pass, and occupant compartment reinforcement. But as you can see, one vehicle translated away from the barrier while the other one rotated. And we think part of this has to do with just the inherent characteristics of a vehicle. So some vehicles, based on their suspension design and other aspects of the upfront structures, might just tend to translate, and others might just tend to rotate about the barrier. And we think that the real benefit is there if you're able to tune your vehicle and your countermeasures to enhance whatever the natural motion of that vehicle is. So a summary of the trends from these redesigned vehicles. Many of the trends were similar to the before-after pairs, which is very promising. We saw that more types of modifications were related to the lowest levels of intrusion. So 33% of our good structures involved all three types of countermeasures. So very cool. 24% of our good structures still exhibited less than ideal dummy-based metrics. And what this means is that there still needs to be an independent focus on the restraint system performance and understanding the kinematics of the dummy for the given vehicle. And again, what we know is that vehicle motion is influencing that dummy motion. When we look at the overall ratings for these redesigned vehicles, we're seeing that most designs are successful in achieving our highest ratings. So the things that people are doing, these different countermeasures that we've studied here, in general are very effective at improving performance, not just improving a little bit, but obtaining our highest levels of performance in this test. So 70% of the vehicles that we've tested that have indicated design changes are coming out with our highest rating of good, and that's really, really promising. What's also really exciting is that we're seeing that many of these changes are coming from mid-cycle modifications. So 60% of the vehicles that have indicated design changes are within a design cycle. So manufacturers aren't having to wait until 3 to 5 years or 7 years down the line when the car is completely modified, redesigned to make these modifications. But most manufacturers are able to now retool and re-engineer these vehicles to gain these highest scores in a short amount of time and before having to wait for complete overhauls, which we think is really cool. It's been something that we've seen progress with every one of our tests, is that manufacturer response is getting faster and faster and faster. And this is really, really exciting to see from our standpoint, to see that manufacturers are making such quick changes and such meaningful changes at the same time. So our conclusions: vehicle manufacturers are responding very quickly to the challenges associated with this test. We see different combinations are effective for small overlap. Improving structure alone does not eliminate all the injury risks, and that the weight change in our redesigned vehicles does not appear to be related to our ratings improvements, and that there are other ways that manufacturers can offset weight additions for small overlap, by doing lighter materials and reductions elsewhere. So I thank you very much for your time today.
And Becky, I want to thank you for that wonderful presentation. Now let's bring up on screen the results of the 2 questions we asked the audience at the beginning of the webcast. The first question polled the audience's opinion on which is the most important way to improve crashworthiness. And the majority of our audience, over 60%, chose effective crumple zones to reduce the forces on occupants. The next most popular response, with about 20% of the audience, was strong occupant compartments that won't collapse in a crash. And our second question was a bit of trivia. When did frontal airbags for drivers and passengers become standard on U.S. vehicles? And most of our audience, about 3/4 of our audience, selected 1999, which of course is the correct answer. Frontal airbags became standard equipment in passenger cars with model year 1998, but on SUVs, pickup trucks, and vans with model year 1999. So, Becky, would you like to comment on the results of both these questions? Are there any surprises here?
Absolutely. I'm actually a little bit surprised that we had 60% for crumple zones and only 20% for stronger occupant compartments, especially since it seems like the trend that we're observing in these small overlaps is to really reinforce that occupant compartment. But we acknowledge that all of these are important and that it's not just one thing that you need to change. And I think that's also one of our messages through this presentation, that it's not just fixing one component, but it's finding the right balance of effective crumple zones, strong occupant compartments, restraint system performance. All of these things really give you the optimized protection level in these types of crashes. I'm glad to hear that about 3/4 of our audience correctly picked 1999 as the year that airbags in the U.S. became standard on all vehicles. What's really cool about airbags is that as technology has advanced, we've seen more and more airbags going into vehicles since then. So it took a very long time to get to that 1999 point where we had all vehicles had both frontal, driver, and passenger airbags. But since then, it seems like with side airbags and rollover airbags and all these new technologies, that airbags have really kind of gone into vehicles at a quicker rate. And now, on average, I think you have 8 or 9 airbags in any car. And we know that they're meaningful. We know that they're important. They save lives. And it's really kind of a cool thing to be able to understand. So thank you.
Thank you, Becky. Becky will be back later for our audience Q&A. And now I would like to ask our webcast audience another poll question. Let's bring it up on screen. Lightweight reinforcement materials is used to reinforce small body cavities. Which of the following statements are true? For this poll, you may select more than one answer. Please choose either lightweight reinforcement material outperforms conventional expandable adhesive solutions because less mass is required to achieve the same performance. Lightweight reinforcement material enhances energy absorption and load transfer between body structure components. Lightweight reinforcement material can join sheet metal components where gaps and joining areas are not suitable for conventional metal joining or adhesive bonding, and or lightweight reinforcement material optimizes body components not traditionally considered in the design process for meeting new safety and stiffness requirements. Thank you. We'll review the results of this poll later in the program. And now, let's welcome our next speaker, Mansoor Murdamati, Chief Engineer at Dow Automotive Systems. Mansour has global responsibility for engineering and application development for Dow Automotive Systems products. He has expertise in design, engineering analysis, and methodology development for body structures and lightweight solutions. He holds 5 U.S. patents and has contributed to several international publications in the area of vehicle body structures, focusing on structural adhesives and reinforcement systems. Mansour, thanks for being with us today.
Thank you very much, Lisa. Thank you very much, Becky, as well for your presentation. It was very, very nice to see all the work that's been done to be able to categorize all the different countermeasures that have been evaluated so far. My presentation today is focused on introducing a material technology based on our Betamate crash-readable epoxy adhesives. And the intent for this presentation is to review the material performance attributes with you, review some of the component level testing studies that we have done internally to be able to quantify the benefits of the lightweight reinforcement material. I will use the component level testing to also show some of the validation work that we have done with the LWR using simulation techniques, because we know that many of the work that's done today in designing and developing vehicles is done through simulation techniques, and we want to make sure that our customer base have the ability to be able to model the product offerings that we have in Dow Automotive for their application needs. And then I want to focus on the specific case studies that we have done with the lightweight reinforcement and wrap up the presentation with some key conclusion. So what is the lightweight reinforcement material itself? So it's based off of our Betamate epoxy adhesive, crash-readable epoxy adhesive that is typically applied in the body shop process, where 2 bodies are assembled together. The sheet metals, you dispense a given amount of adhesives on the flanges, and then you typically weld through those flanges or use other joining techniques. However, when you look at a typical cross-section, in this case a typical B-pillar, you can think about different ways of reinforcing this B-pillar construction. One way to reinforce this B-pillar is put a reinforcement with the structural beta foam in the lower left-hand corner. The other way could be perhaps use the flange bonding adhesives, which is the Betamate epoxy that is used in many of the vehicles today. That's actually been used since the late 1990s. But there are also many areas in the vehicle that the cavities are in place between body components, that those cavities are not necessarily suited for accepting a traditional epoxy adhesive, because the gaps vary quite a bit, and it's also too small to be able to put other conventional reinforcement materials such as the structural beta foam. So the idea here is we wanted to develop a material that is able to be working in those spaces. So these are spaces that are 0 to 15 millimeter in space. Be able to utilize application method that is currently in place today for utilizing flange bonding adhesives, which is streaming, swirling, or applying adhesive via bead. And the idea here is that once the material is applied to one of the components, in its wet state, you're leaving a small gap, so that air gap can be used to drain the E-coat during the E-coat process. But once the body components see the heat in the alpha oven, that kicks off the reaction within the material, and the expansion occurs, and then the inner cavity is then locked with the outer cavity. So that's the concept of the lightweight reinforcement, and to be further explored in this process. The other way of looking at utilizing the lightweight reinforcement in material is thinking about cases where you have a non-uniform gap from one side to the other side, where you may have one side that is less than 0.5 millimeters in gap, and other areas where you have more than 6 millimeters. And you can think about utilizing this type of material to be able to accommodate those gap variations and be able to design the expansion characteristics in such a way that would eliminate the need of having to plug these openings that you may have to do later after in the E-coat process. So it's very, very suitable for being able to accommodate multiple gap variations that could exist between body components. We have also done studies where we can think about not being locked into a given expansion characteristics of the lightweight reinforcement. So what you see here in this picture is a series of coupons with different Betamate LWR grades that have volumetric expansions of 21% on the right-hand side all the way to 164% on the left-hand side, indicating that after the material is fully cured, the material is actually expanding normal to the surface, be able to bridge the different gaps that may exist. But based on those volumetric expansions, you can also have different joint strength properties. So the graph that is shown here is plot of the lap shear strength and T-peel as a function of the volumetric expansion. So the higher the values are, you have lesser the volumetric expansions, and then the higher the values in the volumetric expansions result in the lower strength values. And the idea here is to be able to fine-tune what you need to have from applications perspective that is necessary to make this lightweight reinforcement work. So we do have some flexibility to be able to fine-tune the expansions of the lightweight reinforcement to optimize it for the structure. We've also done this test called the wedge impact peel, where we drive a wedge through a bonded coupon at a speed of 2 meters per second to identify its toughness characteristics in events of impact and peeling. So what you can see here is after the test is over, we have a good permanent deformation of the substrates that is shown on the left-hand side with the impact peel loads of around 9 to 10 newtons per millimeter, which for expandable epoxy adhesives is very, very respectable, knowing that in the world of crash toughened adhesives, those values are approaching 25 newton per millimeter and above. We have also done evaluations against multiple OEM material specifications, looking at the change in properties as a function of different conditions, whether it's humidity, environmental cycles, heat aging, or different salt spray schedules. And what we have noticed is that because of the type of a material that we're using, and its foundation is based off of a Betamate epoxy adhesives, there's minimal change as compared to the parent properties that are measured at nominal conditions and room temperature. Now, one of the issues that always has to be considered is the possible read-through that may exist between utilizing expandable adhesives. That is, one side is against the body side inner per se, and the other side is against the Class A surface. So what we did is we had some positions of our painted vehicles in our lab. We went ahead and put the lightweight reinforcement in the different areas that we were targeting for the application. So these areas are, let's say, the B-pillar, the roof rail, and even the roof bow. We did definitely notice signs of read-through for the roof bow and the roof. However, for some of the other areas along the body side aperture, we were not able to detect any signs of read-through associated with utilizing the expandable epoxy material for these applications. The other thing that we wanted to do is to evaluate the performance of this material at the component level test. So what we developed was the design of the cross-section that you see here, two hat sections that is welded along the flanges to a flat closeout panel. And this is all made up of 0.8 millimeter electrogalvanized steel. with the lightweight reinforcement in between the cavities and comparing that to an empty cavity configuration. Now what you see here is the actual testing results of a dynamic impact, where the top picture is a dynamic impact of that cavity that I showed before without any reinforcement between the inner and outer. And the lower cavity is the same construction, but with a lightweight reinforcement in between on the lower that you see there. And from this video, it's very clear that the lightweight reinforcement is able to provide much higher resistance to these types of loads from the impact characteristics, and the resulting loads and intrusions are much better managed with the lightweight reinforcement. So the results of that test could be depicted by looking at the force deflection diagrams that is shown here. The black curve is the average curve of 3 tests done with empty cavities with no reinforcement, showing a load of 10 kilonewton. The red curve is utilizing an expandable epoxy material that does not have the toughness characteristics, so it's somewhat brittle, and it shows slightly higher load improvement and also a better intrusion. However, with the lightweight reinforcement, which is shown in blue, we are seeing the highest amount of load carrying capacity. So we are seeing an average of over 20 kilonewton and a much reduced intrusion of close to 30 millimeters in this particular type of a test. And the amount of material that we're adding into the system is only about 110 grams of the expandable adhesives, indicating the whole lightweight concept of utilizing a lightweight reinforcement to be able to increase the load carrying capacity significantly. This is the output of some of the correlation work that we did with the lightweight reinforcement using this dynamic test. The pinkish color curve is the results of the predictions, and the other curves are representing the testing conditions that were done for the dynamic impact, and there is a strong level of agreement between the testing and simulation results. We also did the testing against different types of loadings to make sure that the material model that has been developed is able to predict the response of different types of loading conditions, and we were able to show with the quasi-static bending test and even TPL tests that the response is very reasonable, and there's a high level of correlation that could be achieved with the modeling approaches to be identified. Now the question becomes, how does this relate into identifying potential solutions for the vehicle crashworthiness? And as we work with our customers, there are many customers that have already identified solutions, and they're trying to perhaps look for ways of taking weight out or cost out. And we also know that there are some customers that have not reached a stage where they have to do they can do a full redesign, and they're looking for intermediate solutions. And we could also try to identify ways of being able to help both of those scenarios for these different impact events. To show that, so this is perhaps could be applicable to a side impact, IIHS side impact, where a B-pillar reinforcement is already utilized. They're meeting the requirement, but the idea here is, how do I use the lightweight reinforcement to take as much weight out as possible for this B-pillar construction? And if I were to take this B-pillar construction and then subject it to 3-point bending loads, one could expect a given bending moment characteristics and also force deflection characteristics. But now the idea becomes, how much thickness can I reduce for those B-pillar assemblies? And then where do I place the lightweight reinforcement? So in this particular case, we are putting a lightweight reinforcement between the body side outer and the B-pillar outer reinforcement and the B-pillar inner and the B-pillar outer reinforcement. But the net result is a 1 kg weight savings because we are able to take the thicknesses down to the lowest possible and achieve a 1 kg mass savings with just only adding 197 grams of material at these two locations, and also maintaining the same bending as well as bending moment at force deflection diagrams. Now the idea here is now try to see what we can do from identification of possible solutions for the narrow offset. So the previous work that I showed was on the component level, but I can also tell you that the same approach that we utilize from a modeling point of view can be extended into the full vehicle perspective. So we had in our position a full vehicle model that we used as the baseline. And with that full vehicle model, we looked at two different solutions. One solution, as is shown in the upper right-hand corner, is the Betamate epoxy adhesives flange bonding. So these are crash durable adhesives that are placed between the body and white flanges in combination with resistance spot welding. And then we also identified all the body and white cavities around the occupant compartment that fall into that space of 0 to 15 millimeters. And we did a couple of different simulations. One simulation was looking at the lightweight reinforcement by itself. The other one's looking at the adhesive by itself, and the last one combining the two solutions together. And it's also worth noting that we further optimize the locations of the lightweight reinforcement on the body side to the one that you see on the lower right-hand corner, which is about 0.9 kg per side, and the amount of toughened adhesives that we utilize is about 100 meters of adhesives across all the body and white flanges. So these are the pictures from the simulations of comparing the baseline on the upper left-hand corner to baseline plus adhesive bonding on the upper right-hand corner, which you can see there's definitely some signs of improvement in terms of the occupant areas where the rocker is more intact. When you add the Betamate lightweight reinforcement by itself, that's the lower right-hand corner. And then when you add the Betamate flange bonding as well as the lightweight reinforcement, which is the lower left-hand corner, you can see the effect is definitely visible from the final deformed shape perspective of the baseline, comparing it to the baseline plus those solutions. And you can see visually from these pictures that both of those solutions are actually improving the compartment significantly. Now, what that means from an intrusion perspective, that is shown here. Now, we're looking at 4 different curves, looking at different intrusion points at different locations. The red curve is considered the baseline, and you can see the baseline vehicle has some areas that are in the acceptable category. There are some areas that are in the poor category. And then when you add the crash durable adhesives plus the lightweight reinforcement, all the intrusion points, with the exception of the rocker panel, have reduced significantly, all in either the good range or in the acceptable range. And there are some areas in the vehicle that could benefit by the crash durable adhesives for the flanges, but there are also some areas in the vehicle that could be benefiting from the lightweight reinforcement between the body side outer and the body side inner components. And the idea here is now what a particular area of the vehicle needs a particular type of intrusion improvement, and how this type of a solution can be used to further optimize the vehicle that is being worked on. So again, there are some folks that have identified solutions, and they're thinking about taking weight out, and there are some folks that have trying to identify solutions, and perhaps some of them are metal, some of them could be non-conventional, but this definitely fits in a non-conventional category that could be considered very early in the design process. So in conclusions, what I've been hoping that I could demonstrate today, that there are options that our automotive customers can utilize, from looking at adhesive bonding using beta-mate epoxy adhesives, as well as the beta-mate epoxy adhesives with the expandable characteristics that could be used to reinforce body in white sections that haven't been perhaps considered before for crash and safety applications. And what we have also been able to show here, based on these case studies, that the amount of material we're adding to the system and the performance benefits we're gaining is significantly improved. And with that, that concludes my presentations, and I will pass it back to Lisa.
Thank you so much, Mansoor. Excellent presentation. Now let's bring up on screen the results of our last poll question, which was, of the following statements, which are true about lightweight reinforcement material? And as we can see, the most popular answer, about 70% of our audience chose lightweight reinforcement material enhances energy absorption and load transfer. The second most popular answer, with about 60% of our audience, was that it optimizes body components not traditionally considered in the design process. Then another 45% of the audience chose that it outperforms conventional expandable adhesives, and about 40% said it can join sheet metal components. So, Mansoor, how did our audience do with this poll question?
Well, actually, I think they did very well. I think tacking on to what Becky showed in the previous presentation, where the occupant compartment is one of the key areas that needs to be reinforced, we'll be able to show that if you're able to utilize components such as the body side outer and tie it back to the rest of the structure, you're able to enhance the overall load carrying capacity, which is really, really good to see. And I'm also quite pleased to hear that the toughened epoxy adhesive systems, or toughened systems, have better load carrying capacity than the unconventional or the traditional ones that are perhaps people maybe most familiar with. But it's really nice to see that the audience also recognizes the need for being able to reinforce the key areas such as the occupant compartment of the vehicle.
Thanks, Mansoor. It's now time for our audience Q&A. Please send us your questions by using the Ask a Question box on the screen. And our first question goes to Becky. It is, will the Insurance Institute for Highway Safety conduct right side small overlap tests in the future? And if so, why do we need to test the right side?
Well, this is a very timely question because we're actually beginning a research program to study right side impacts, focusing on small overlap and moderate overlap right now. So by the end of the summer, we're going to have a research series conducted where we understand what is the structural challenges associated with the right side that are different from the left side. And so this is probably going to be our up-and-coming next program to really understand from a crashworthiness standpoint. It's important because even though we don't know how many passengers are riding in vehicles, we do still know that about 2,000 belted right front passengers die every year. And that's something we'd like to reduce.
Very good. Thanks, Becky. A related question from our audience says that the Insurance Institute for Highway Safety has a range of tests, and this person wants to know what's next besides the right side that you just talked about. What's next?
So what we're also studying is we're going back and looking at real-world injuries for side impact and trying to understand, is there anything that we're still missing through our side impact test? And so this summer we're also going to be running some side impact research tests. So stay tuned for that as well.
Very good. Becky, here's another question for you. Someone in our audience writes, it's not clear if the best strategy is to glance off or rotate on impact. Glancing off gives the lowest delta V, but occupant motion is not desirable. So, which would you recommend?
Well, and that's the interesting thing. We're not really sure which to recommend either, but we think based off of what we're starting to observe, that it very much depends on what the vehicle inherently wants to do to begin with. So the most effective designs are those where the countermeasures enhance what the vehicle was doing interacting with the barrier even before they made design changes. So those that glanced and you added countermeasures that made it glance more seem to perform better than those that glanced to begin with, and then the countermeasures made it glance less. That kind of thing. So we don't design cars, we just test them, but from our outside observations, it seems to be that we don't prefer one or the other, but that it's vehicle specific.
Thank you. Mansoor, you have the next question. Someone in our audience wants to know, how about bonding performance deterioration during vehicle life? And they're asking, is initial bonding performance and 10 years later the same? Mansoor?
Yeah, that's a very good question. The nice thing about what I presented here is the technology has been something that's been used in the industry since the 1990s. There has been also some full vehicle teardown studies. One of them which we did about 10 years ago of taking a vehicle that has been driven in a hot climate conditions and humid conditions, and taking those vehicles apart and really looking at the joint performance associated with those vehicles. So the technology is used for a long time. We have seen very minimal degradation in terms of the joint properties for those vehicles that has been evaluated. Then that tells us that what we have in place is actually a working solution in the industry. Obviously, we're working very closely with our customers to make sure that the product satisfies all their requirements. And the other key aspect is that the expandable version is based off of the chemistry. The same chemistry has been used in the industry for many years. So the things associated with the long-term performance, obviously we don't have 10-year data at this point in time, but we have very high confidence that it can meet all the expected requirements.
Thank you, Mansoor. Here is another question for you. Someone in our audience wants to know, are there any current production vehicles using the Betamate technology?
Yes, like I said, the Betamate technology has been used since the late 90s. It started with many of the European-based OEMs. But over the last 10 years, there's been a significant number of vehicles that are produced in U.S. by North American OEMs that are taking advantage of the Betamate epoxy adhesives. There are no one to date that has utilizing the lightweight reinforcement concept associated with the Betamate adhesives yet.
Thank you, Mansoor. Here's another question for you. Is the narrow offset intrusion comparison based on CAE models? If yes, how was the material characterization of the foam implemented in the CAE model? So
yes, all the results that I showed were off of the full vehicle simulations. Before we could do the full vehicle simulations, we had to spend quite a bit of time in making sure that we understand the characteristics of the expandable epoxy is not a foam, even though it's perhaps what you might consider as a seat foam or other types of foam systems that expand quite a bit. But it is a model that has been identified and verified against many coupon testing. many different types of loading conditions, as well as component testing that was done under full dynamic conditions. So we are utilizing essentially the same assumptions that we utilize for those testings, and just carrying them over to the full vehicle simulations level.
Very good. And with that, we're at the end of our webcast. I want to thank both our speakers for their excellent presentations today and for answering these questions from our audience. A survey will pop up on everyone's screen immediately following our program. Please tell us what you thought of our webcast by answering its 3 short questions. This webcast will be archived and available for viewing on the SAE website. An email will be sent to everyone who registered for today's program as soon as the archive is ready. Remember, you may download PDFs of the PowerPoint slides by clicking the links on the left-hand side of your screen under Event Resources. I'm Lisa Arrigo with SAE International. Thanks for joining us.